Well, this is something we need to think about in terms of how we get our energy. It's really is an energy-based solution, and we've been using this solution for so long. I've obviously chosen the picture above to show us what will be happening in terms of combustion. Now, combustion is another name for burning. So it's involving fires and involving releasing energy. But we're going to look at that in some detail now, and also a quick reminder about what's going on in terms of balancing equations and chemical changes and things like that as we go through. Alright, so let's start. Now, burning is obviously one way or another word for combustion. And as you can see over here, we've got three things required. We've got to have a heat source, normally a flame of some description, the oxygen present, and something to burn, or a fuel. And then combustion occurs, and out the other side we get material, it can be some gases or some liquids or whatever coming out. Mainly gases come out, some solid particles too as well. And this heat, and of course we've got light there as well. We should have light coming in because it is another nice thing that comes out of most of the burning combustion places we have. A lot of light comes out. But the thing that we want, the energy we really are after, is this heat. And then as you see down here, this heat then is used to burn more oxygen and fuel. And so it's a self-perpetuating cycle once we start it. Now that can be good or it can be a bad thing. Alright, so don't forget, way back when, you might have seen that you need three things to start a fire. You need the air, oxygen in particular, you need something to burn, and you need a source to start the burning. Okay, so this is what's going on, and let's look a bit more depth now. So, to summarise, combustion is another name for burning. That is something we need to do, but in science we'd prefer you, and in this topic and this section on thermal energy, we'd prefer you to talk about combustion, because that is how we normally gain the energy from the fuels we burn. And we've been doing this all the way from before the Industrial Revolution. Just during the Industrial Revolution we changed the fuel. We went from more a timber-based or wood-based thing to a coal and other sources. Right, the main reason combustion exists is to release the extra energy that's in that fuel. Remember, we've got any fuel we've got is going to be chemical energy. Now it is stored in the bonds of the chemical. So what actually happens is combustion helps us to release that energy that forms in the bonds. Right, as we've said, combustion requires oxygen. No oxygen, right? No burning. That's why we have things like our fire blanket. Our fire blanket is to stop oxygen getting to the fire. A fire extinguisher we often use is a carbon dioxide one, and the carbon dioxide surrounds the fire and doesn't let the oxygen get to it. Right, so what you've got to do if you want to put a fire out or extinguish a fire is to stop one of those things, and we often try to stop oxygen getting in there. Now, two things we must look at. One is when there's lots of oxygen. So if I've got heaps of oxygen, we say that the complete combustion has occurred, and we will get all of the energy, pretty much all of the energy out of that fuel. But sometimes we don't, and we don't have enough oxygen, and we have incomplete combustion, and then we get other things, but our energy output that we want to, for heating, for cooking something, for making something move, for providing kinetic energy, whatever, we don't get as much. So incomplete combustion is a bad thing. We don't get as much with it. This is particularly a problem in cars. If we haven't got the car set up properly, because a car works by effectively having an explosion between petrol, which is the fuel, plus oxygen, and then I use a spark plug to ignite it. And there's my fire cycle. And we have combustion going on there. Now, if it's all working properly, I have complete combustion. But when the car is not set up properly, I have incomplete combustion. And then, as we're going to see, we end up with all sorts of other things which are not quite as good for us. Plus, we're wasting money. Right, so let's have a look at the basics of this again. Remember I said to you we're going to be thinking about chemical change. Now, a chemical change means that we start off with something and we have a rearrangement. So a chemical change is going to rearrange the atoms. But I want you to remember there is no loss of atoms. So the law of conservation of mass occurs. So no atoms destroyed. Or added for that matter. Alright, now the basic thing is then, when we're doing all this and showing what we think is happening, we use a chemical equation. And a chemical equation can be like the one down the bottom here, which is a word equation. And we're going to ask you at various times this year to do word equations, like this one, and more symbolic equations. In other words, tell me actually what the fuel is and then add the symbols of these and formulas. All right, now what you want to remember is this side, the left-hand side, is what we're using, or reactants. They're needed. The right-hand side is what we make. Now this part here about we're rearranging these atoms to make these things. So all of the carbon in the carbon dioxide came from the carbon in the fuel. All the oxygen in the dioxide here, and in the H2O water came from this oxygen. So we've got to make sure we have the same number and type of atom on both sides of the equation. That's when we add the symbolic equation, and that will be in a moment. We'll look at that. So make sure you remember this side is reactants, this side is products. So if we look at these things, let's go to a typical thing. Now, most people, if they're going to a barbecue, they use a gas barbecue these days. There are other types of barbecues, of course, but we use gas barbecues a lot. Now, the gas that we normally burn is propane. Now, I know that propane has got 3 carbons and 8 hydrogens in it. Alright, so as you can imagine, there's quite a few little bonds there in it. We can actually work it out if we actually draw its structure. So there's my 3 carbons. Now I know all this sort of stuff from all my years. Now every carbon has got the hydrogens attached to it. The hydrogens don't attach to each other, they attach to the carbons. And the carbons also attach to each other. So look, we've got 1, 2, 3 carbons. 1, 2, 3. And we've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds holding that propane together. And that means each one of those bonds contains energy, stored energy. That's how chemicals store their energy. So we've said, or I've done this equation for us, we've said that if I have 1 lot of propane, I need 5 lots of oxygen. Remember, oxygen gas in the air is O2. So I need 5 lots of oxygen gas. And what I make is 3 lots of carbon dioxide and 4 lots of water vapour. Now it's a vapour. We don't normally actually see water coming out when we burn. It comes up as water vapour, and then it can be recondensed and goodness knows what, but that's what's going on with it. So again, we've got 1 lot of propane mixes with 5 lots of oxygen to make 3 lots of carbon dioxide and 4 lots of water. So let's have a look at how many atoms we got here. I got 3 carbons. Over here I've got 3 times C, so 3 carbons. I've got 8 H's. I've got 4 times pairs, so I've got 4 pairs of H's here. H2 is a pair, so I've got 4 lots of H2, that means I've got 8 hydrogens. Hey, it's balanced so far. Then I've got 3 lots of O2 here, okay, and 4 O's, or if you like, 2 lots of O2. That's the same as 2 by O2 there. So now I've got 3 here, plus 2 is 5, and I've got 5 over here. Hey, I've obeyed the law. And I've obeyed the law of conservation of mass. So that means I have neither created or destroyed any atoms in my reaction. So in a normal chemical reaction, we don't create or destroy, we simply rearrange. Alright, let's look at the next bit. So there we go. So that is when we've got enough oxygen, that last one. But what happens if we don't have enough oxygen? Well, then we have what's called incomplete combustion, and we form other things. Now, carbon dioxide is not a great thing. That forms with complete combustion. It's not a magnificent thing for us, but it's far, far better than this stuff. Carbon, it gets into our lungs and causes problems. These are carbon atoms or carbon particles. Soot, if you like. And if we breathe that in, yucko, our lungs soon start to clog. And this stuff, even though we've got 1 less oxygen here, CO, carbon monoxide, it's lethal. It'll kill us. So if we don't put enough oxygen in what's going on, then we can be in all sorts of problems. Now this is a big problem in cars. If we don't look after our car properly and somehow the carbon monoxide we are making gets into the car itself, then we can be in real problems. We can die. So here's what I'm doing again. Now I'm going to rearrange. I'm going to do the same sort of stuff. This time I've got propane again, but I've got less oxygen. Last time we had 5 lots of oxygen. This time I'm only combining the 1 lot of propane with 3 lots of oxygen. And now I make some soot, some carbon particles, some carbon monoxide, and some water vapour. And if I go through the same process I did a minute ago and count the number of atoms, we find that that is absolutely correct. I've got equal number of atoms on both sides, so we say it's balanced. So we've got equal atoms on both sides, or numbers of atoms. So I've got an equal number of atoms on both sides, and so it's balanced. All right, that's what we're trying to do. But incomplete combustion doesn't have to be a bad thing. Now, we don't much use it here, even though we do tend to use it more for other things than its intended use. If I take something like, this is a whole heap of bits of wood, and I put them in a big container, and I stop air getting to it, right? There's air inside this container, yeah, that's fine, but I don't let any more in. So I put the lid on, and then I start burning it. All right, so we're doing incomplete combustion. There is not enough air getting to it, and the good thing is that we make things like charcoal. Now, charcoal still has energy stored in it. So I can take charcoal home, and I can light it up. I can have a fire starter or some other method to light it up. And I can cook my dinner on it. And a lot of developing countries, this is how they do it. Right? They don't have the massive supply of the energy on tap we do in our Western societies, so they have to work with what they've got. And one of the things they do have is charcoal. And as I said here, it's done totally by having not enough oxygen in there. If there's enough oxygen in there, I don't get charcoal anymore. Some of you might have seen a barbecue like this one. These little charcoal bricks here, these little charcoal things here, we have to put a lighter. In other words, we have to put some other chemical in there and then use a match to light it. And eventually the charcoal will start burning itself. And that becomes our barbecue. Alright, but we can use anything. It doesn't have to be timber. I believe they've used exotic things like coconut shells and husks, various other plant parts that have gone in there. And as long as we stop too much oxygen coming in and we pack these in nice and tight, we can end up with some good charcoal to burn. And on that note, we're going to stop it.